Okay, this is going to be a quick video explaining the basics of Cartesian and polar coordinates, how to convert from one to the other, and some basic problems with some basic uses of them. Required skills: in order to do this, you need to know the basics of Pythagorean trig. Only writing on triangles, nothing more complicated than that. For example, here find x, which is sort of a basic trig. I won't do it, but if you do it, x should be 14 centimeters exactly. Okay, let's get started. So these are Cartesian coordinates. They're good for straight lines, but really bad for circles. So quick example, x is 3, y equals 4. That just means on my x coordinate, I go 3 squares across. On my y coordinate, I go 4 squares up. So it's that point there. Dead straightforward. Slightly harder, same idea, just y equals 4. That's going to be all the points for which the y coordinate is 4. So if you want to plot that, you would first find the y-axis, find where 4 is, and it's going to be a straight line across that. So again, really easy to do a straight line. However, looking at polar coordinates, these are slightly different. So rather than x and a y coordinate, you have an r and a theta. That's basically going to be an angle and a radius. So for this coordinate here, we have a radius of 4. That means on my big circular grid here, I'm going to be 4 squares away. Okay, I'm going to be on this line of 4. And also my angle is 60 degrees. Really important, the way these angles work is 0 always starts on the x-axis, and then as theta gets bigger, you always go up or you start going anti-clockwise. I think just going up from the x-axis is the way it works in my head. So here radius is 4, so we're on this circle here, and the angle is 60 degrees, gives us this coordinate here. And one more, if I just had r equals 4, that's going to be all points which the radius is 4. So that'll basically give us this entire circle. So again, like I said, that's really good for circles and really bad for straight lines. So doing a straight line with polar coordinates is quite awkward. But if I wanted the same equation using Cartesian, it would look like this. So it's just a lot neater to do it in polar coordinates. I'll do one more example of a graph in polar coordinates, because this is a fairly nice example. So again, a fairly straightforward equation, basically just r equals theta divided by 90. So that means the radius is going to be the angle divided by 90. So the way we're going to work this out is we're going to plot a few points, and so you can see some sort of pattern going on. So first of all, what happens if theta is 0? Well, if my angle is 0, then 0 divided by 90 is still 0. So that tells me the radius is 0. So my angle is 0, my radius is 0. Whenever your radius is 0, that means you are at the origin. So your first point is at the origin. I'm going to jump a bit. The next point I'm going to look at is what happens when theta is 45 degrees. So going back to my equation, this is now 45, and 45 divided by 90 is a half. So when theta is 45 degrees, my radius is going to be a half. So on my graph, 45 degrees is this line here, and I want a radius of a half, which is that little line here. Okay, keep going. Next one we're going to look at is going to be theta equals 90 degrees. Plugging this in, 90 divided by 90 is 1. So the radius is going to be 1, which leaves my next point here. I'll skip a bit. If theta is 180 degrees, I now have 180 divided by 90, which comes out as 2. So the radius is 2. Next point I would do would be theta equals 270, and 270 divided by 90 gives us 3. And if theta is 360, 360 divided by 90 gives us 4. So my next 2 points will be here and here. Now you want to join those together, and you want to join together each successive value of theta. So basically I'm going to sort of join this to this, then this to this, this to this, and so on and so forth. So doing that, I start at 0, I then go to 45, I go to 90, and as we can see with this graph, we're basically spiraling outwards. If I did more points, the spiral would just keep getting bigger and bigger and bigger. Okay, the base sort of just goes to infinite in size. Again, that's a super simple equation in polar coordinates. If I wanted that in Cartesian, it would look something like this mess. And again, looking at that Cartesian equation, even though they're the exact same thing, it's really obvious to kind of say this is going to be a spiral. As the angle increases, the radius increases. It makes sense that's going to be a spiral. But looking at this, it's not at all obvious what's going on here. For the most part, it just looks like a massive mess. Okay. Some useful skills is converting from Cartesian to polar and polar Cartesian. This is where the Pythagorean trick's going to come into it. So if I've got the coordinate 3, 4 labelled here on my graph, I can convert it to polar coordinates. What I'm going to do, I'm going to make a triangle. The x coordinate is 3, so that means I've gone 3 squares along. The y coordinate is 4. What I want to work out, first of all, is going to be the radius. The radius is going to be this length here. And you notice this is a right angled triangle. That means you can use Pythagoras. And that is going to be r squared will equal 3 squared plus 4 squared. Working that out, r squared is 25. So here my radius is 5, which basically means I am 5 squares from the origin. Next, working out the angle, we're going to use trigonometry. Again, the angle I want always starts on the x-axis and always goes up. So I want to work out this angle here. Okay, that's going to be my theta. To do this, the easiest way to do it is always use trig and always use tan. So you should know from SOHCAHTOA that if you have tan of the angle, that will equal the opposite over the adjacent. Here the opposite is 4 because it's opposite the angle, and the adjacent is 3. So I know that tan theta is going to be 4 over 3. If you want to work out the angle itself, we just inverse tan. So theta will be the inverse tan of 4 over 3. And you can work that out just by typing it into a calculator, which I don't have with me right now, but I think it's something like 57. And that's how you convert from Cartesian to polar. Slightly more useful is doing the exact same thing the other way around. So I want to convert from polar Cartesian. I've got this polar coordinate, which says my radius is 2 and my angle is 30 degrees. So that's going to be that point here. So on the line of radius 2 and I'm 30 degrees up. And I'm going to do the exact same thing as before. I'm going to draw me a nice looking triangle. I'm going to fill in what I know. Radius is 2, I've got a right angle here, and this angle here is 30 degrees. Now I can use trig twice to work out both my x coordinate and my y coordinate. Okay. So I will do the x coordinate first. If you look at this, to do SOHCAHTOA, we want to work out what we have in terms of opposite, adjacent, hypotenuse. The opposite is here. The hypotenuse is always the longest, which means the adjacent is here. So I have adjacent and hypotenuse. That means we are using Ka. So it goes SOHCAHTOA. So therefore we know that, let's do it a different way. So the way I always treat SOHCAHTOA is to think of them all as triangles. Okay, so this is the Ka triangle. If we want to work out what A is, we're going to cover it up. And on the bottom we're left with C and H. That means you want to do cos times the hypotenuse. So to work out the adjacent, we're going to do cos of the angle times the hypotenuse. So let's write that down. To work out the adjacent, which is x in my case, because x is adjacent, that will equal cos of 30 times hypotenuse of 2. Working that out on a calculator is going to be 1.7 something. Okay, and we can then do the exact same thing to work out the y coordinate. So we're done with x, we want the y coordinate now. This time we have opposite and hypotenuse, so we are going to use SOH. And the exact same way as before, we want to work out the opposite, so we cover O up, and we're left with sine of the angle times the hypotenuse. That means y is going to be sine of the angle, which is still 30, times hypotenuse, which is still 2. And this comes out as 1. Okay. That's in a specific case. What is really useful and comes up quite a lot is having a formula for that in general. So if I go to this picture here, I want to convert this random coordinate, we're going to call it r theta, into x's and y's. Okay, and do the exact same thing we were just doing. Make a nice little triangle. I have r and I have theta. And I'm going to work out these two things. So for my x coordinates, we have opposite, no we don't, we have adjacent and hypotenuse. So therefore, I'm still using K. Let me just write them all down for now. So I'm using K for this one. If I want to work out x, which is my adjacent, that's going to be c times h. So that is going to be cos of the angle, we just call it cos theta, times r. Okay, and normally this is written r cos theta. We can then do the exact same thing for my y coordinate. For that, I want to work out the opposite, so I'm using the SOT triangle. Opposite would be sine times hypotenuse, which means y is going to be sine theta times r, and again that is normally written as y equals r sine theta. So this here is how you convert from polar coordinates to Cartesian coordinates. Okay, and that can be really useful. So if I want to describe some points along a circle using Cartesian coordinates, I can use the method really easily. So I'm going to say I want 6 points. I want points every 30 degrees. And I want my circle to have a radius of 4. Okay, so I'm going to have these, I'll just at the top half, these 7 points altogether. Okay, working that out for each case in trigonometry each time will be really awkward. But if we use polar coordinates, this is really straightforward. So I know for this first coordinate, let me just number them really quickly. So I know for the first coordinate, radius is 4, and my angle is 0. So that means x would be 4 cos of 0, and y would be 4 sine of 0. You work those both out, you get x equals 4y equals 0, which is obviously true because it's down there. Then for the second point, we know radius is still 4, and now the angle is 30 degrees. And we do the exact same thing. Okay, and the advantage of this is that you can code this really quickly. You can just tell the computer to run through the angles, and I'll do that happily, rather than faffing about with kind of individual trig cases for each separate scenario. And again, I've forgotten the angle, whatever 4 cos 30 turns out to be. It'll be something like 3.3-ish. Lastly, we can do the exact same trick to describe points along an oval. Okay, so again, it can be useful for whatever code needs you have for it, or whatever math problem you're doing. So I'm going to say, I want this oval here. Oh, probably better than that. So we basically we've got the big radius is going to be 4, and we've got a small radius of 2. So it kind of looks a bit like an eye. So we're going to work out this equation. We're going to do it straight on the fly, and we're going to use the same tricks we're doing just over here. So typically, we have x equals r cos theta and y equals r sine theta. And what I said a second ago, my big radius, I'll call this r1, is 4. And that is the radius which occurs on my x coordinate. So that means my x equation is going to be x equals 4 cos theta. I can then do the exact same thing for my small radius. For my small radius, call that R2. That has a radius of 2. So here, y will equal 2 sine theta. And now if you use those and run through the values of theta, for each different value of theta, that will basically trace points along this oval. And again, this is a huge headache in Cartesian coordinates, but in polar it's very intuitive and very straightforward. Okay, that's all I'm doing for today. Hope you found it useful.